Hello everyone. In this video, I will be talking about how to use the Google App Engine platform along with the Google Cloud Endpoints service to provide an API backend usable by any number of clients, both mobile and web. The App Engine API backend will use the Objectify framework to model its entities and interact with the data store. All of the App Engine code will be written completely in Scala, and this video assumes that you are familiar with using Scala to develop on the App Engine platform. If you haven't seen my previous video, I provide a quick introduction to writing Scala applications with App Engine, and the accompanying documentation and sample code fill in all of the details. This video, much like my last, has extensive documentation and sample code that go into great depth about the ins and outs of using these technologies together. Of course, you can check the description for this video for links to all of these resources that I'm mentioning. Now, this video also assumes that you're familiar with using Objective-C to develop iOS apps and thus doesn't explain any iOS-related concepts. My motivations for this project were really to see how all of these popular technologies and languages work together and tease out the subtleties of developing applications using them. Because Objectify and the Google Cloud Endpoints service were designed specifically for Java, I first wanted to figure out if they could be used with Scala and what extra configurations were necessary to make this happen. Being new to App Engine development myself, I then wanted to assess the benefits attained by using these technologies. I also wanted to find out if there are any limitations introduced by using these technologies together, and, if so, any workarounds or future solutions to get around them. To accomplish all this, I wrote a complete sample application, a multiplayer tic-tac-toe game that lets players sign in with their Google accounts and play against other Google users. While I only wrote the iOS client application, the Scala API backend could support Android and web client applications as well. Without further ado, I want to show off the iOS tic-tac-toe client in action. The API backend is already being hosted on the App Engine production servers, so I just need to start running my Objective-C tic-tac-toe client in the iOS simulator like so, and I'm good to go. Also, in order to demonstrate the multiplayer nature of this application, I will be using an actual iOS device off screen to pose as my opponent. You'll just have to trust me on this one because I unfortunately cannot display this device on my screen as well. Okay, so when we launch the app, the first thing that needs to be done is to log in. So I'm just going to provide some sample credentials here that I used to test with this account. Of course, it's got a simple password. Now once I log in, I'm presented with this dialog that essentially just asks whether or not I'm fine with the application using my personal data, like my email address. So once approved, we can see that the two sections of the main table view start to fill up with entries. Now this is just some data I placed into the data store to make the screen a bit more interesting. But if we click on one of these past games, we are presented with a screen where we can see the final game board along with some supplementary text describing the outcome of the match. Now if we go back to the main screen and press the plus button, we are presented with a new game, and apparently we're playing against nobody. Actually, this demonstrates one of the key features of the tic-tac-toe application. If there is nobody that wants to play a game of tic-tac-toe, then the player can still start a game and take their first turn without even needing an opponent, like so. Now, when somebody else does finally decide to play some tic-tac-toe, like for example me right now on this off-screen device, they will be placed into this game. So I've just made my move, and now if I hit the refresh button, you can see the title updates, and I now have my opponent. So I'm just going to continue here making some moves so you can sort of see what's going on. When I hit refresh, the move I made off screen has been updated. I can make another move here. And as you can see, I have to hit the refresh button to find out whether or not my opponent made their move. So this project wasn't meant to be about creating wonderful iOS apps, and thus a polling solution wasn't implemented, although it could have been. Likewise, no in-app notifications are being sent, but this project was meant to explore the iOS side of things. So also, if I go back to the main screen here, you'll see this new game has updated to its current state, and no new backend API calls need to be made. So when I click on the game again, the local copy will also be updated if the App Engine copy of the game has changed. So for example, you can see here, it's clearly not my turn. I can go back, make a move off screen, click on the game, and we can see it's now my turn. So now when the game finishes, for example like so, the game viewing screen is completely disabled. And if we go back to the main screen, we can now see that the game has moved down into the scores section. So we can click on it, and there you have it, the tic-tac-toe game that I just played against myself. Alright, now before we take a look at what is going on in the back end, I want to briefly introduce the technologies and explain how they fit in the tic-tac-toe application. So the first technology I want to introduce is the Google Cloud Endpoints service. This service provides a tool, which I'll refer to as the Endpoints tool, that one can use to generate the API configuration files needed to host the API backend on App Engine and the client libraries needed to access these APIs from mobile and web clients. This tool is located right here in the App Engine Java SDK in the bin, and we can see there are two different versions of this tool. Now I'll be using the endpoints.sh version because I am running OS 10 on my computer. Now the endpoints tool analyzes annotations that you place within your code to determine what APIs you are exposing. So from the command line, you run the endpoints tool like so, specifying the full class name of each class that you want the tool to run on, all separated by spaces, as you can see here. So the tool creates some API discovery and configuration files, as well as a Java client library compressed into a zip archive that can be used by both web clients and Android clients. Now the API discovery files can be used to generate the iOS client library, and you need to upload these discovery files along with the .api configuration file to App Engine to use your application as an API backend. Now, while these APIs could be accessed by clients without the auto-generated client libraries, you would have to write a lot of boilerplate code to serialize and deserialize the objects being passed back and forth between the two endpoints. Why reinvent the wheel? Unfortunately, the Endpoints tool was written for use with Java and doesn't recognize any Scala classes when run without modification. Fortunately, a simple change to the endpoints.sh code, like so, that pulls in the necessary Scala jars to the class path, is all that is needed to get the Endpoints tool to work properly on Scala code. And as you can see here, I've just hard-coded the path to the Scala directory on my own computer. You need to do the same for your own, obviously. Now, the other necessary configuration common to both Java and Scala is regarding the deployment descriptor file. So we've got this entire section here that's needed for Google Cloud Endpoints, and this is all explained in Google's documentation. But this line right here in particular is where you specify the full class names of each class that implements any APIs. Finally, you need to generate client IDs so that other applications can access your APIs. These client IDs are obtained through the APIs console, which requires creating a separate project to manage the APIs that you want to access. So you can see here I'm in the tic-tac-toe endpoint project I've created to manage my APIs I'll be using. Once you're in the main menu of a project, you just go down to API access, and from here you can create any of the client IDs that your application will need. Alright, now the iOS client library can be generated using a tool included with the Google API's client library for Objective-C called the Service Generator. And to be able to use the auto-generated iOS client library, you need to pull this Objective-C client library into your iOS application anyway. Now this can be done in a number of ways, and I discuss pulling the library into your application and using the service generator tool further in my documentation. One nice thing to know about this tool is that when you run it, it will tell you if any changes were made to the files created the last time you ran it. So you can see if I run it at the command line here, press enter, we can see no changes were made from what's already on disk. So I know I don't need to update any of the iOS files within my Xcode project for my iOS application. Now this behavior is only possible if you output the service generator files to the same directory. As you can see, I have an API directory for that. And if you just leave a copy of the files there at all times. But this is really helpful as it lets you know which files to update when you add or remove some APIs. The other major technology being used within the tic-tac-toe application is the Objectify framework. Now, I specifically use the Objectify version 4.0b3 jar, which can be found in the Maven Objectify repository. Now you also need to include the Google Guava jar because it is a dependency of Objectify, and you'll find links to these jar files within my documentation. Despite being designed for Java, it's amazing how seamlessly Objectify works with Scala. So there's a few key points of interest. To auto-populate the ID field of a long ID, you need to directly use the java.lang.long type. And this is because Scala's long does not allow you to initialize to a null value. And initializing to a null value is how you get the auto-populating behavior. Now, this is common to both Java and Scala, but you'll notice these no-arg constructors. These are just needed for Objectify to be able to create instances of these classes within the database. Another point of interest is regarding the type method. So the type keyword is a reserved word in Scala. So to use the type method of the Objectify service, you have to surround it with backticks like so. Which is a little ugly, but it gets the job done. So now one of the limitations introduced by using Objectify with the Endpoints service is the inability to use Objectify's ref and key classes. These classes are provided by Objectify to help define complex relationships between the entities in your application. The Endpoints tool throws an exception when a parameter or return value of an annotated API contains either of these two types. So this includes an object with a ref or key member variable. And the tool fails because it cannot properly serialize an instance of either of these two classes when the data is passing between the API backend and client. So to illustrate as an example, I've created this test method here, which essentially just grabs a score from the database and creates a score ref from it and returns it. So if I go to the command line here and run the Endpoints tool, the first thing it's going to tell me, while it's running here, is that it can't find the Objectify ref class. Now this is the same issue that we had with Scala. So if we go into the Endpoints tool here and add in the Objectify jars to the class path, you'd think we would be all good to go. Fortunately, if we run the Endpoints tool again, we'll now get a much different error. Now this time it's telling us the parameterized type class ref, essentially ref of score, is not supported. So a suggested workaround for this issue would be to instead separate your entity classes into an internal representation that gets saved into the data store and an external representation that's only used to pass data between the API backend and the client. So the external representation would only need to contain the ID of the internal representation along with any other information that the client app would need. And you could still retrieve the internal representation in the API backend when a request comes in using that ID stored in the external representation. Now that you're more familiar with the different technologies, let's take a look at what's happening on the back end. So because I'm hosting the API backend on App Engine rather than locally, I have access to the wealth of information provided by the administration console. So if I go to the admin console in my browser here, the current project is the Tic-Tac-Toe API backend. So from here I can learn a lot about how my application is behaving in the production environment. But I want to specifically draw your attention to the application logs. Now, as you might expect, within this section you can see all of the messages that the application logs. So every request that the API backend receives will be logged and displayed here, and we can see that this includes all of the API calls that were being made while I was playing that game of tic-tac-toe. Because I added some extra log messages to the API backend for some of the methods, we can see there's a bit more useful information in some of these sections than others. For example, here we can see I've output a message on the info level stating the game that was just updated. But one thing that we can see with all the requests is that they all finish with this 200 response code indicating success. And we can even see how long they took to complete and whether there was a significant size associated with the query. Now another useful screen is the data store viewer. So go over here, data store viewer, and from here we can see all the entities that are currently in the data store, and sure enough the game that I just played against myself is in here as well, and along with of course a bunch of other games that were all, well, me playing against myself. But from this screen you can even run queries or create entities directly from right up here. You can see you can use some GQL to run a query, or we can create a game entity if we wish. Now, while the admin console is definitely useful, most developers need a tool that they can use to test their APIs locally when they are developing them. So this is where the APIs Explorer tool comes in. So first, we just need to start our development server, just like with any normal App Engine application. And just wait for this to start running here. When it does finish, we should be able to go to the localhost 8888 where the server is running, and actually it's saved right here. Go to the /_/a sorry, I said that wrong. /_AH/API/Explorer, and you'll be presented with the Google APIs Explorer tool. So from this tool, we can explore our API and send API requests to the local API backend and receive the response through a user interface that's much easier to use than curl at the command line. Another benefit we get from this is being able to authorize requests using OAuth. So the OAuth 2.0 scope to use for a Google email account can be found in the iOS client code. You just copy paste that into here, hit authorize, and it'll ask you to sign in using your Google email account. In using all of these technologies to create the tic-tac-toe application, I discovered a few different limitations, both due to the inherent behavior of these technologies and their behavior when used together. So the first limitation specific to two of the technologies, Objectify and Google Cloud Endpoints, and their lack of support for the use of abstract base classes. So with Objectify, this is merely an issue of annotations. So if the base entity class, this game class for example here, is labeled with the abstract keyword, Objectify will throw an exception when it tries to instantiate an object for this abstract class. Now this issue is being addressed likely through the use of a separate annotation to denote an abstract base class in a polymorphic hierarchy, something along the lines of @entityBase, for example. And as I said, this issue is already being addressed by the Objectify developers. Now in the meantime, a possible workaround for this issue would be to simply remove this at entity notation from the base class, label it abstract, and place this at entity notation on all of these subclasses. The disadvantage to this approach is that this will create a separate data store kind for each of these subclasses, and also requires an amount of code repeat proportional to the amount of code in the abstract base class, since you'll have to override the member properties for Objectify to pick up on them. Now, while this workaround could have been implemented for tic-tac-toe, there's another limitation introduced surrounding abstract base classes by using the Google Cloud Endpoints service. So, as evidenced by this finder create game method, an abstract base class is useful because it can be used to return an object with a type corresponding to any of the concrete subclasses. In this case, either a pending game or a current game. Because of how the Endpoints tool generates the API client libraries and configuration files, the underlying type of the object returned by this finder create game method will always be game. So when the client sends a game object back to the API backend, it will have an underlying type of game and not one of the concrete subclass types. So if we made game abstract back in the game.scala file, this would cause the JSON serializer to throw an exception complaining about how it cannot serialize an abstract class. A workaround for this issue is actually exactly the same as the one suggested to work around the issue of endpoints not being able to serialize the ref and key classes. So you could use an external representation to pass data between the client and API backend, which wouldn't need to worry about abstract base classes, and an internal representation where such an abstract base class wouldn't cause any issues. Of course, this workaround relies on the mentioned Objectify support for abstract base classes being implemented.